Hi all, welcome back to another session of Ball Computer. In this session, I am discussing about the topic that is chemical kinetics. So coming to the first topic, that is what is chemical kinetics. Chemical kinetics is a branch of chemistry which deals with the study of rate or speed or velocity of a chemical reactions. It also deals with the factor which influences this rate or speed or velocity of a chemical reactions. Kinetics is derived from a Greek word that is kinesis, which means movement. So it also deals with the mechanism in which how a reactant is converted into product. We all know that a detailed description of each step involved in the reactions is termed as the mechanism. So chemical kinetics also deals with the study of mechanism of the reactions. Coming to the next topic, that is what is rate of chemical reactions. Rate of chemical reactions is the amount of chemical change per unit time. That means when a chemical reactions is proceeding, definitely the concentrations of the reactants tends to decrease and concentrations of the products tends to increase. So, rate of a chemical reactions can be defined as the change in concentrations of any one of reactants or products in per unit time. So, consider the reactions A to B. Here A is the reactant and B is the product. So, rate can be expressed either in terms of the concentration of reactant or concentration of the product. So, in terms of concentrations of the reactant, the rate can be expressed as minus delta concentration of A divided by delta T. Why negative sign means when a chemical reaction is proceeding, definitely the concentrations of the reactant tends to decrease. That is why due to the decrease in the reactant concentration, we are putting the negative sign. Similarly, in terms of product concentration, we can express the rate of chemical reaction as rate is equal to plus delta concentration of B divided by delta T. Because the concentration of the product is increasing in the formations of a chemical reaction. So, the rate of chemical reactions in terms of product means we are putting a positive sign. Again, coming to the unit of a chemical rate of a chemical reactions, we know that the concentration is usually expressed in terms of mole liter inverse and time which is expressed in second. So, the unit of rate of chemical reactions will be mole liter inverse per second. So it will be mole liter inverse and second inverse will be the unit of rate of chemical reactions. So this way of expressing the rate of chemical reactions is termed as average rate of chemical reactions. But it is not convenient to express or it is not useful to express the rate of reactions in average rate of reactions because rate of chemical reactions will not be constant throughout the entire span. That means at each time interval there will be a change in rate of chemical reactions. So it is conveniently expressed in terms of instantaneous rate of chemical reactions. That means at each moment of time there is a rate of change in chemical reaction. So it is expressed as minus d concentration of A divided by dt or plus d concentration of B divided by dt. That means in each moment of time there is a change in concentration. That is why a small time interval represents the d. That is termed as the instantaneous rate of chemical reactions. So consider this hypothetical reaction, that is AA plus BB gives CC plus DD. So in these reactions, how to represent the instantaneous rate of chemical reactions we can look. So we already discussed that rate of chemical reactions can be expressed in the concentration of reactant or product. So in terms of reactant, we can express as rate is equal to minus 1 by A. Here there is a coefficient, so we have to divide the coefficient. That is rate is equal to minus 1 by A, the concentration of A divided by dt. And again, in terms of B, we can express as minus 1 by B, the concentration of B divided by dt. In terms of product, that is, we can express a rate of reaction as we are putting positive sign, therefore rate is equal to plus 1 by C, the concentration of C divided by dt, or we can express in terms of D as plus 1 by D, that is the concentration of D divided by dt. So if they are asking the rate of chemical reactions, we can express the rate of chemical reactions as in these 4 ways. But if they are asking the question that is rate of disappearance of A means we don't want to express this coefficient, that is we can express as minus dA by dt. There is no need of dividing the coefficients. Similarly, if they are asking the rate of disappearance of B in this chemical reactions means we can express as minus dB divided by dt. There is no need of this coefficient, that is minus 1. That is 1 by B is not required. That is we can express as minus d concentration of B divided by dt. Similarly, if they are asking that is rate of formation of C means we can express it as plus dc divided by dt. There is no need of this coefficient, that is 1 by C. Similarly, if they are asking the rate of formations of D means, that is we can express as plus dd divided by dt. There is no need of this coefficient, that is 1 by d. Next, we can discuss how to plot the rate of chemical reactions graphically. So consider this reaction, that is A to B. Here, we can plot graphically either in terms of concentrations of the reactant versus time or concentrations of the product versus time. So here, in terms of concentration of reactant versus time, that is concentrations of reactant is plotted on the y-axis and time is plotted on the x-axis. So we all know that when the chemical reactions is proceeding, the reactant concentration tends to decrease. So first, the reactant concentration is high. So when the chemical reaction is taking place, that is when we are finding the rate of chemical reactions, the concentration of the reactant tends to decrease at each point of time and then the graph will be like this. So we can find the slope of this reactor curve and then we can find the rate of chemical reactions. Similarly, when we are plotting the graph between concentration of the product and time means initially the concentration of the product will be 0 because there is no, first the concentration of the reactant is increasing. When the chemical reaction takes place only, the product concentration is high. So first the concentration of the product is 0. Then as the chemical reactions take place, then the rate of chemical reactions is found to be, that is the product concentration is slightly increasing and then the rate of chemical, the graph will be like this. Then again by finding the slope, we can find out the rate of chemical reactions. Next, we can discuss a question, that is express the rate of following reactions in terms of concentration of reactant and product. So the reaction is 2N2O5 gives 4NO2 plus O2. So rate we have already discussed that it is the change in concentration of the reactant per unit time, or it can be expressed in terms of product means change in concentrations of product per unit time. So here in terms of reactant, when we are discussing, we have to put a negative sign, and here we have one coefficient, that is here it is minus 1 by 2. So rate can be expressed as minus 1 by 2 d concentration of N2O5 divided by dt in terms of concentration of reactant. Again, in terms of product means we can express the rate as plus 1 by 4 dNO2 divided by dt. Again, in terms of oxygen concentration, we can express as rate is equal to plus d concentration of O2 divided by dt. Again, suppose if they are asking what is the rate of disappearance of N2O5 means we don't want to express this coefficient, we can express as minus d concentration of N2O5 divided by dt. Similarly, if they are asking the question, that is what is the rate of formation of NO2 means, we can simply express it as plus dNO2 divided by dt. Similarly, if they are asking the rate of formation of O2 means simply dO2 divided by dt. Next, we can discuss what are the factors influencing the rate of chemical reactions. There are several factors which influences the rate of chemical reactions. Some of the important factors are the concentration of the reactant, then presence of catalyst, then third one is the temperature and surface area, and last it is the presence of light or exposure to radiations. So coming to the first factor, that is concentration of reactants. That is, if the concentration of the reactant is increases means, that means rate of chemical reactions also increases. Again, coming to the second factor, that is presence of catalyst. Catalysts are added to chemical reactions means to increase the speed of chemical reactions. So the presence of catalyst increases the speed of reactions by reducing the energy requirement for the chemical reactions. Again, coming to the third factor, that is temperature. When temperature is increased means the rate of chemical reactions also increases. That means rate of chemical reactions become almost double for every 10-degree rise in temperature. So rate of chemical reactions also increases when temperature is increased. Next factor is surface area. That is, greater the surface area of the reactant, the speed of chemical reactions also increases. That means if you are taking a crushed wood as well as a log of wood, this will burn faster. We found that crushed wood will burn faster than that of the log of wood because crushed wood occupy a larger surface area. Therefore, it will increase the speed of chemical reactions. So, greater the surface area, the rate of chemical reactions also increases. Last factor is presence of light. That is, if our chemical reactions is exposed to light, or if our chemical reactions proceed with some light or any radiations, it will increases the speed of chemical reactions by reducing the energy. So these are the some factors influencing the rate of chemical reactions. First is the concentration of the reactant, next is the catalyst, temperature, surface area and presence of light. So let us first discuss in detail the first factor influencing the rate of chemical reactions, that is effect of concentrations of reactant on rate. That is, we have observed that the rate of chemical reactions increases when the concentrations of the reactant are increasing. So, according to law of mass actions, for a chemical reaction, AA plus BB gives product. In these reactions, according to law of mass action, the rate of chemical reactions is directly proportional to the molar concentrations of the reactant. That means rate is equal to concentration of A raised to A into concentration of B raised to B. That means here the concentrations terms are represented based upon the stoichiometry of the reactions. But for the same reaction, we can express the rate law as rate is directly proportional to concentration of A raised to X into concentration of B raised to Y. In this rate law or in this rate equation, the concentration terms actually depend upon the rate of the reaction actually depends upon. The concentration terms represents the rate of reactions actually depend upon. That means rate law is determined experimentally, and moreover this X and Y, that is exponents, are also determined experimentally. It is not depending upon the stoichiometry of the reactions. So this proportionality equation can be converted into mathematical form by multiplying to a constant. That is, rate is equal to K into concentration of A raised to X into concentration of B raised to Y. So this K is a constant and which is named as, that is, which is known as rate constant or specific reaction rate. And this above equation, that is, this equation is termed as rate law or rate equation. And we can define this rate constant as when we take the concentration of A and concentration of B is equal to 1, then the rate of chemical reactions become equal to the specific reaction rate or rate constant. So, rate constant can be defined as the rate of chemical reactions when the concentrations of the reactant are taken as unity. So, consider this reaction, that is 2NO plus O2 gives 2NO2 gas. In these reactions, we found that experimentally the rate law is equal to, that is rate is equal to K into concentration of NO whole square into concentration of O2 raised to 1. That means here the exponents, that is X and Y, are same as that of the stoichiometry of the chemical reactions. That is here 2, here 1. So same we are getting in X and Y term, that is exponents we are getting same, that is 2 and 1. So it is depending upon the stoichiometry of the reaction, but the rate law it is found to be experimentally, it is like this. But when we look the reaction, next reaction, that is chlorination of the chloroform, that is CaCl3 plus chlorine giving CCl4 plus HCl. In this reactions, the rate law is found to be rate is equal to K into concentration of CaCl3 whole raised to 1 and chlorine concentration is raised to 1 by 2. That means it is not based upon the stoichiometry. That is why we have told that the rate law is determined experimentally and these exponents also X and Y are also determined experimentally. It is not based on the stoichiometry of the reactions. Next, we can discuss the order of the chemical reactions. So consider a hypothetical reaction that is AA plus BP gives the product. And the general rate equation can be expressed as R is equal to K into concentration of A raised to X into concentration of B raised to Y. And we have found that this X and Y can be same or cannot be same and does not depend upon the stoichiometry of the reactions. And when we take the sum of these exponents, that is X plus Y, we will get the order of the reactions. That means the order of the reaction can be defined as the number of the reactant molecule whose concentration changes and determines the rate of the reaction is termed as the order of the reactions. Or it can be defined as the sum of the power in which the concentration terms are raised. And in determining the rate, expression is termed as the order of the reactions. So order of the reactions are determined experimentally, and it can be 0, it can be fractional order, or it can be negative, or it can be any whole number. So let us discuss some example for the reaction, that is decompositions of N2O5, that is nitrogen pentoxide. Here N2O5 giving 2NO plus half O2. Here rate expression is found to be K into concentration of N2O5. That means order of the reaction is, exponent is here it is 1, so order of the reactions is found to be 1. We can consider the next reaction, that is decompositions of ammonium nitrate in aqueous medium. Here ammonium nitrate giving nitrogen and nitrogen gas and water molecule. Here also the rate expression is found to be K into concentrations of ammonium nitrate. So here also the order of reaction is 1. So these two reactions are the example of a first order reaction. We can consider the second reaction, that is the formations of hydrogen iodide by the interactions of hydrogen and iodine. Here the rate equation is found to be R is equal to K into concentration of H2 and concentration of I2. So here exponents, that is concentration of H2 exponent is 1 and concentration of I2 is 1 raised to 1. So order of the reaction will be 1 plus 1, that will be equal to 2. So this formations of hydrogen iodide is an example of second order reactions. And consider the decompositions of nitrogen dioxide. Here 2NO2 giving NO plus O2. Here also rate expression is found to be K into concentration of NO2 raised to 2. Here also the exponent is 2, so order of the reaction is found to be 2. So these two are the example for a second order reactions. So we have already discussed that the order of the reaction can be whole number, it can be fractional, it can be zero order, or it can be negative value also. So let us discuss some example for an order of the reactions become fractional. So here consider the decomposition of acetaldehyde at 723 Kelvin. It results in the formations of methane and carbon monoxide. Here the rate law is found to be R is equal to K into concentration of CH3CHO whole raised to 3 by 2. That means the order is becoming 3 by 2, that is a fractional order. Again next, when we look the next reaction, that is formations of hydrogen bromide. Earlier we have found that the formations of hydrogen iodide is an example for a second order reactions. So there will be automatically a confusion for an HBr also, but HBr, when we are looking the reactions, the rate law is found to be K into concentration of S2 into concentration of Br2 whole raised to half. That means the order will be equal to the sum of the power of the exponents, that means 1 plus 1 by 2, that will be equal to 3 by 2. Here we are getting a fractional order reactions. That means it is an formations of HBr is an example of a fractional order reactions, and the order is found to be 3 by 2. Next we can discuss some example for a zero order reaction. It is consider the decompositions of ammonia in the presence of catalyst, that is either gold or platinum. So decomposition of ammonia to nitrogen gas as well as the hydrogen gas. Here the rate is found to be rate is equal to K into concentration of ammonia raised to 0. That means here the reactant concentration is independent. That means here order is found to be 0. Again, consider the formations of hydrochloric acid by photochemical combinations of hydrogen and chlorine. Here the rate is found to be independent of the concentrations of hydrogen and chlorine. That means here the order of the reaction is found to be 0. So there are some reactions which is having a zero order also. These are the some examples, that is the decompositions of ammonia in the presence of catalyst either gold or platinum, and again the photochemical combinations of hydrogen and chlorine to form HCl is also an example of a zero order reactions. Next we can discuss how to find the unit of a rate constant or specific reaction rate, that is K. Generally, we can take for an n-order reaction, we can express the rate equation as R is equal to K into concentration raised to N. So, on that equation, K is equal to rate divided by concentration raised to N. And we have already discussed that rate unit is, that is rate, it can be defined as a change in concentration per unit time. So, the unit of rate will be mole liter inverse second inverse divided by concentration, it is expressed in mole liter inverse. So here it is the nth order, so mole liter inverse raised to n. So on simplifying we will get mole liter inverse second inverse divided by mole raised to n liter raised to minus n. So it will be equal to, on simplifying, that is mole raised to 1 minus n liter raised to n minus 1 second raised to minus 1. So for n order of the reaction, the unit of rate constant will be mole raised to 1 minus n liter raised to n minus 1 and second raised to minus 1. So suppose if you want to find the unit of rate constant for a zero order reaction, here n will be equal to 0. Then on substituting, we can get the unit of rate constant as K is equal to mole raised to 1 minus 0 liter raised to 0 minus 1 second raised to minus 1. So the unit of rate constant for a zero order reaction will be mole liter inverse second inverse. Suppose our order of the reaction is 1, then n is equal to 1, and substituting here n for n it is equal to 1, then we can find the unit of rate constant and it is found to be equal to second inverse. So for a zero order reaction, the rate constant unit will be mole liter inverse second inverse. For a first order reaction, the unit of rate constant is found to be second inverse. So for any order reaction, we can just substitute the order in this, that is value of n, we can substitute in this and then we can find out the unit of rate constant. Next we can discuss about the molecularity of a chemical reactions. Molecularity of the reactions can be defined as the number of molecules or atoms or ions which collide simultaneously to bring about the chemical reactions are termed as the molecularity. So that means how many molecules are participating or how many chemical species are participating in a chemical reactions, that gives the molecularity. So consider this reaction AA plus BB gives the product. Here A mole of A collide with B mole of B gives the product. So molecularity can be equal to A plus B. Just adding the stoichiometry of that reactions gives the molecularity. So the molecularity can be a whole number only. It cannot be 0, it cannot be fraction. If it is 0 means there is no reaction taking place. That means there is no reactant, means there is no chemical reaction. So molecularity cannot be 0. Moreover, it cannot be fractional and it can be whole number only. Again, it is a theoretical concept. Just after balancing a chemical reactions, we can find out the molecularity. But order is determined experimentally. So it is not a theoretical concept. Again, consider some example to find the molecularity of the reactions, that is O3, decomposition of ozone to give O2 and oxygen atom. In these reactions, there is only 1 mole of ozone. So the molecularity is found to be 1. That means this is an example of a unimolecular reactions. Again, consider the decompositions of hydrogen iodide. Here, 2Hi giving H2 plus I2. That is, we have to balance the reactions, then we have to find the molecularity of the reaction. Here 2 mole of Hi is converting to H2 and I2. So molecularity is found to be 2. So it is an example of a bimolecular reactions. So let us discuss the difference between the order and the molecularity of the reactions. So order can be defined as a sum of the power of the concentration terms, that is sum of the power of the exponents in which concentration terms are raised in determining the rate law expression is termed as the order. But molecularity means it is a number of molecules or ions or atoms which collide simultaneously to bring about the chemical reactions are termed as the molecularity. Again, we have found that order can be zero order, it can be whole number, it can be fractional, it can be negative. So, but molecularity, we found that it can be a natural number, it cannot be zero, it cannot be fractional also. And again, when order, coming to the order, it is determined experimentally. It cannot be a theoretical concept. So, it is found out experimentally, but molecularity, it is a theoretical concept. Just after balancing a chemical equation, we can find the molecularity of the reactions. Again, when we discuss the mechanism, by determining the order, we can get some idea about the mechanism of the reactions. But coming to the molecularity, it does not give any idea about the mechanism of the reactions. So that is all in this session. Hope you like this session. Stay tuned for the next session. Till then, bye.